In this lesson, we are basically reaching the end of our journey when it comes to factoring. There are more techniques to learn, but we'll save them for grade 12. So what do we know so far? We hopefully have mastered factoring, factor by grouping, factoring simple trinomials, and factoring complex trinomials. So in this lesson, we are going to learn 2 more techniques, and that's essentially it. Okay, so these factoring techniques, I put quotations here, and we call them special. Now, why are they special? Because we can only apply these 2 techniques when the expressions are very special. Okay, and we'll talk about why these expressions are very special. So the first type of expression is called a difference of squares. So first of all, let's look at these 2 factors, a plus b and a minus b. Okay, there's a clear relationship between these 2 factors. The terms are the same, but for the first factor, you're adding the 2 terms, and for the second factor, we are finding the difference of the 2 terms. So if you have 2 terms that are designed like this, then they are called conjugates. Sorry, if you have 2 factors that are designed like this, they are called conjugates. Okay, so a plus b and a minus b are conjugates. Now what we're going to do is we're going to multiply, expand and simplify when we multiply 2 factors which are conjugates. And I'll show the intermediate step. So a times a is of course a squared minus ab plus ab minus b squared. So this minus ab and plus ab, they cancel each other out, right? Because they're opposites. So all you're left with is a squared minus b squared. Now I'll tell you why this is very special in a moment, but whenever you multiply a pair of conjugates, what you're going to get is this expression called a difference of squares. So let's first explain to ourselves, why is it called a difference of squares? Well, look at the 2 terms, a squared and b squared. They are perfect squares. And what's the operation between the 2? It's a subtraction. So it makes sense to call this expression a difference of squares. Okay, so whenever you see a difference of squares, what you can do is express it as a product of a pair of conjugates. Okay, so let's fill in the blanks, and then I'll mention something else. So a difference of squares can always be expressed as a product of a pair of conjugates. Okay, so why is a difference of squares very special? Because if you think about it, if you multiply a binomial by another binomial, you're never going to get a binomial unless those 2 binomials you're multiplying are conjugates. Okay, so that's what makes a difference of squares very special. When you multiply a binomial by another binomial and you get a binomial, then it has to be a difference of squares. Because usually when you multiply binomial by binomial, you get a trinomial. So the only way to get a binomial is if you have a difference of squares. And that's what makes the expression very special. So I'll say one last time. When you multiply binomial by binomial, you usually get a trinomial. But if you get a binomial, it's a difference of squares. Okay? So let's see. Let's factor the following expressions. So difference of squares. Let's check. Is my first term a perfect square? Yes. My second term a perfect square? Yes. So are the conjugates? We have to be a little creative. What multiplies to x squared? X and x. What multiplies to 9, right? So you can say, oh, let's square root 9, which is 3, right? Of course, 3 squared is 9, right? So some students put 9 and 9 here. Please don't put 9 and 9, because if you expand, you get 81. You want to find the square root of 9, right? You want to find the conjugates, so plus, minus. So I've created my pair of conjugates. And when in doubt, expand. Okay, so let's keep going. Is this a perfect square? Yes. Is this a perfect square? Yes. So is this a difference of squares? Yes, because it's a subtraction. So let's ask ourselves, how do I multiply to 4x squared? Okay, it's 2x times 2x. How do I multiply to 36y squared? So you could say square root 36y squared, and that's going to be 6y. Oh, I just noticed something. I was being very silly. And now let's express as a pair of conjugates. When I wrote down 2x plus 6y and 2x minus 6y, I just noticed I was so silly. I forgot to common factor first. So if you missed a common factor like I did, what you have to do now is factor the factor 2 from each of these factors. So that will be x plus 3y. So I factor 2 from 2x plus 6y. And I factor 2 from 2x minus 6y. So now 2 times 2 is 4, of course. There we go. So we still found the correct answer. But you know what? I'm going to do this again. I'm going to do it one more time. So this time I'm going to start off by factoring or common factoring that 4 first, because that was silly. You always check if there's a common factor first. And then perfect square. So x plus 3y, x minus 3y. Difference of squares, express it as a product of a pair of conjugates. So I'm going to jump back to the first example. If you have a hard time finding out or determining that you should write a 3 here, what you can do as your first step, instead of just factoring or finding the conjugates, what you can do is write it like this. Instead of writing 9, I'm going to write it as 3 squared. Once you know what's being squared, it should be very, very clear that the conjugates should be x plus 3 and x minus 3. Okay, the factors must be x plus 3 and x minus 3. So ask yourself, really, you're asking yourself what is being squared, and then you can create the two factors. Okay, all right, over here, x to the power of 4 minus 1. You know what? I'm going to write down x to the power of 4 is really x squared, right? Because power of power in grade 9, when you have a power of power, you multiply the exponents. And 1 is, of course, 1 squared. So if you write it like this, it's perfectly clear that you have a difference of squares. There's no doubt, right? There's no doubt. So now I'm going to express it as a product of a pair of conjugates. So this must be x squared plus 1, x squared minus 1. Okay? And unfortunately, on the test, this would be like a 2-mark question or a 3-mark question. And students always, and they stop right here. Okay? They think it's fully factored. But that would be a mistake, and you'd lose 1 mark at least. So here, x squared minus 1, you can keep going, right? That's another difference of squares. You can keep factoring, right? X squared plus 1 I can't touch because that's a sum of squares, and there's no factoring technique for that. But for difference of squares, oh yeah, x plus 1, x minus 1, right? So if you can keep going, you have to keep going. Okay? All right. Let's do this one, D. Now I know it looks a little weird, but this is a difference of squares, right? Let's write our conjugates here. A minus B plus B plus C times A minus B minus B plus C. Right there. Okay? That's the conjugate. But of course, or those are the conjugates. But of course you can simplify, right? So this first factor simplifies to, well, minus B plus B is just 0. So it's A plus C. And over here, this is going to be A minus 2B minus C. Okay? I distributed and simplified in one step. So if you find that too hard for yourself, just take it in 2 steps. Okay. What about this one? Common factors? Nope. So let's just do it. So, you know what? I'm gonna write 1 step to help you out, because a lot of students have a hard time seeing what's being squared. So it's 2a minus 3 squared. Okay. Minus 3b cubed squared. Okay. Now that you know what's being squared, it's very obvious that you have a difference of squares. And it's very obvious what to write in terms of the factors. So it's 2 times 2a minus 3 plus 3b cubed 2a minus 3 minus 3b cubed. Okay. So now I'm going to expand and simplify. So it's going to be 4a, so 3b cubed plus 4a minus 6. And this is going to be minus 3b cubed plus 4a minus 6. But of course, we want to factor out -1, so this factors in standard form. Okay, so 3b cubed plus 4a minus 6, and then 3b cubed minus 4a plus 6. Beautiful. All right, all the terms are in, all the factors are in perfectly. And you know what, if you're ever in doubt, I know it's time consuming and tedious, but what you can do is expand all this and you'll get back to the very beginning. Okay, F. Let's take a look. Is that a perfect square? No, 3 is not perfect square, but what can we do? We can factor. Right? 3 is a common factor. And then I see a difference of squares here. So it's going to be a minus 3 plus 1, and then a minus 3 minus 1. So it's going to be a minus 2, a minus 4. Beautiful. Perfect. Okay, so for all of these expressions, they look different, but you're just manipulating how they look. You're manipulating how they look, but mathematically speaking, they're very much the same. Okay, so that was one of our special expressions. The other special expression is what we're going to see here. So if you expand a plus b all squared, you can do the math, and we've done it earlier in the unit. You'll get a squared plus 2ab plus b squared. If you expand a minus b all squared, you'll get a squared minus 2ab plus b squared. Now we call these trinomials, okay, whether it's a squared plus 2ab plus b squared or a squared minus 2ab plus b squared, a perfect square trinomial, okay? So we have a special name for this expression as well. This trinomial is very special. We call it a perfect square trinomial because they were obtained by squaring a binomial, right? The only way to get one of these expressions, whether it's a squared plus 2ab plus b squared or a squared minus 2ab plus b squared, is if you squared a binomial. So it makes perfect sense to call it a perfect square trinomial. Like if I show you the number 9, you call that a perfect square because 3 times 3 is 9. If I gave you 16, that's a perfect square. If I gave you 25, you call it a perfect square. Well, I know it's weird to call this a perfect square, but it is, right? In fact, a better name, instead of just calling this a perfect square, would be to call it a perfect square trinomial, okay? So really relate this trinomial with 9 or 16 or any other perfect square, okay? All right, so the hard part about perfect square trinomials is identifying when you have one, okay? You have to be able to spot one really quickly. It's like you're finding Waldo. So I suspect that a perfect square or a trinomial is a perfect square trinomial when the first and last terms are perfect squares. Okay. Because most of the time when I see a trinomial, the first and last terms are not perfect squares. Okay, but if they're both perfect squares, then I start getting very suspicious. Okay, so let's take a look. First term, x squared. Is that a perfect square? Yep. How about the last term, 9? Is that a perfect square? Yes. So now I have to check the middle term. I have to check the middle term to see if it's going to be the right term to make it a perfect square trinomial. Okay, but I'm very suspicious already because the first and last term are perfect square trinomials. So how do I check? So what you have to do is understand what A and B is. Okay, so what I mean by A and B is the terms that make up the binomial being squared. So if the first term is x squared, then A is equal to x, right? Because x squared is a squared, that means a must be x. Now b squared is 9, so b must be equal to 3. So usually I write this in my head, by the way, but I'm just showing you because we really want to be able to identify this together. So 2ab, okay, we want to check the middle term. Is it 2ab? So 2 times x times 3. That's 6x. So guess what? Do I see 6x here? Absolutely. So guess what? This is a perfect square trinomial. X plus 3 all squared. It's plus because it's x squared plus 2ab plus b squared, right? It's either x squared, a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. So if it's minus 2ab, then it's going to be a minus b all squared. If it's plus 2ab, then it's a plus b all squared. So this is plus 2ab essentially. So it's a plus b all squared. Okay, by the way, students will say to me, I didn't need you to tell me that. Just ask yourself what multiplies to 9 and adds to 6. Yes, that is correct. But later on, we'll do some harder examples where you really want to be able to identify perfect square trinomials. Okay? Alright, 4x squared minus 12x plus 9. Once again, I'm getting quite suspicious that this is a perfect square trinomial. The first term is a perfect square. The last term is a perfect square. So I'm very suspicious. So let's check. So if the first term is 4x squared, a is 2x. If the last term is 9, then b is 3. So now it's time to check. 2ab. Is 2ab 12x? Let's see. 2x times 3. Oh, absolutely. It is 12x. So guess what? This is a perfect square trinomial. This trinomial was obtained by squaring a binomial. So what was the binomial being squared? 2x minus, because it's minus 12x, 3. Okay, and when in doubt, expand and check your answer. Let's keep going here. This is definitely not a perfect square trinomial because the first term is not a perfect square. But you know what I can do? I can common factor it too. Oh, now this one is a perfect, is it a perfect square? Let's check. So this is x, a is x, and b is 9. So 2 times x times 9, 18x. Yes, 2 times x times 9 is 18x. So this is a perfect square trinomial, okay? If you have a hard time with that, just write down what a, b, and 2ab is. Okay, so that is a perfect square trinomial. So there we go. All right, is this a perfect square trinomial? Well, my first term is a perfect square. My last term is a perfect square. You know what? Let's help you out. A is 5x, right? Because a squared is 25x squared, then a must be 5x. B is 11y, because b squared is a 121y squared. What's 2ab? Is it negative 110, or is it 110xy? Let's see. It is, which means this is a perfect square trinomial. So 5x minus, because it's minus 110xy. So this trinomial is in the form of a squared minus 2ab plus b squared, which means I can factor it to a minus b all squared, which in this case is 5x minus 11y all squared. Okay, let's speed up a little here. Factor 2 is a common factor. And this, believe it or not, looks just like a. I know the letters are different, but it's really the same question. It's a perfect square trinomial. All right, here. Is this one? Let's see. 3x times 4 is 12x. 12x times 2 is 24x. Absolutely, perfect square trinomial. Once again, I got very suspicious once I saw 9x squared and 16. 3x plus 4 all squared. Beauty. Okay, now we're getting to some harder examples. So on the test, you'll see some factoring questions, or I call them combos. You need more than one technique. Okay, you've done some questions, like I would argue C is a combo question. Okay, E is also a combo question. You have the common factor, and then you have to factor perfect square trinomial. Now G is a more challenging combo question. Okay, so with G, the first thing you have to see is just look at the terms. And when I look at the terms, I see something very beautiful here. I see a typo I made actually. I'm so sorry. I'm just gonna change that to a 2 there. Okay, so now let's take a look at it again. And yeah, let's take a look at it again, and hopefully we see something really pretty here. Okay, so I'm gonna speed up a little and tell you that there's actually a perfect square trinomial here. So what I'm gonna do is I'm gonna factor out -1 from these 3 terms, the last 3. And you see, then you have a perfect square trinomial. So I'm gonna factor that. So a squared minus 2ab plus b squared is a minus b all squared. And what do you see now? Z squared minus a minus all of a minus b squared. That's a difference of squares. So express it as a pair of conjugates. And of course, just clean that up, simplify that. So a minus b plus z minus a plus b plus z. Factor out -1, clean up that factor. Beautiful. So this question is on the harder side of the factoring questions because you have to spot that perfect square trinomial. And once you're able to spot the perfect square trinomial, you'll then be able to create your difference of squares. Okay, how about this one? Believe it or not, this is actually a perfect square trinomial. Okay, this is a perfect square trinomial. Because I'm going to write the perfect square trinomial and hopefully that'll help you see it. It's a minus b squared minus c squared all squared. Okay? If you expand this, you will get back to the original expression. And now I'm going to clean that up. I'm going to expand. Oh, wait a second. What do you have here? You have another difference of squares. You have a difference of squares. This is beautiful. Okay, so factor this in, what's being squared is a difference squared. So it's all of this being squared. So this is a minus b plus c, a minus b minus c. So all of that's being squared, and then that means I square each factor. Beautiful, beautiful. That was very pretty. I really like that actually. Okay, and it's all about practice because I can see a different squares because I've seen the expressions. It's very easy to miss that boat. But like I said, if you do enough repetitions of these factoring questions, you'll be able to see the patterns. You'll be able to spot the perfect square trinomials. Okay, let's do this one here. Right away, I see a common factor of 2. Oops. And then I see something else actually. I see that these last 3 terms will make up a perfect square trinomial. And then, of course, I can turn that to a binomial squared. And then I have a difference of squares. Isn't that pretty? So 2x plus y plus 1, 2x minus y minus 1. Beautiful. Well, those last three questions were really nice. Those are the combo questions that, unfortunately, I would say students struggle with, and they're only struggling because they can't spot the perfect square trinomial. They can't spot the difference of squares. Anyways, we have lots of great questions for the homework, so we can do those questions, and really it just takes repetition. And that's it. So we've reached the end of the journey for factoring, at least for this course. And this lesson covers those special expressions. Okay, so the special expressions are a difference of squares. The only way to get a binomial when you multiply two binomials by one another is if the two binomials were conjugates, and that will result in a difference of squares. So that expression is very special. And these two expressions are also very special because they're called perfect square trinomials. And the only way to obtain these two trinomials is by squaring a binomial. Okay, so hopefully you understand what makes these expressions so special, and that will really help you when it comes to factoring them.